Again, but this time, finiteness properties and complex hyperbolic lattices.
Well,
Yeah.
thank you. I would like to thank the organizer for inviting me. I'm happy. It's my third time in Montreal. First time I give a talk here, but third time here. Also, I apologize because there are a few people in the audience who already heard me talk about this, maybe even twice for one person at least. So I'm sorry. Okay, and as Danny said yesterday, we love and celebrate Brady Morse theory, but in this talk you will see classical Morse theory, old-fashioned stuff. Okay, so we saw in the previous talk, in Bruno's talk, that there exists G, hyperbolic, and H, a subgroup of G, with H of finite type, not hyperbolic. Okay, so the goal here is to give further examples of finitely presented non-hyperbolic subgroups of hyperbolic groups, but they will not be of finite type. So maybe recall, I don't know if maybe probably someone said this last week, but if G is hyperbolic, then G is F infinity, so Fn for all n, and actually of finite type if it's torsion free. Okay, so you prove this using the Rips complex. And so so the goal is to build more finitely presented subgroups of hyperbolic groups which are not hyperbolic. And also, I mean, you will never see me write a presentation. Okay, so as Bruno said, in large dimension, if you want to study hyperbolic manifolds, the main construction is to use the arithmetic construction, and I will deal with complex hyperbolic manifold, and it's even more true in the complex hyperbolic world compared to the real hyperbolic one. So recall this question of Brady. So Brady, in a paper from 1999, he gave an example of a subgroup of a hyperbolic group, which is finitely presented, but not F3, actually not FP3. And there were further examples of subgroups like this later on by Loda and Kropoller. And in the same paper, he asked, is there, so if you take an integer n, which is at least 3, here's a G hyperbolic, and H, a subgroup of G, with H Fn of type Fn, and not Fn plus 1. Okay, so for n equal 2, this is what I just said. Yes. So this was the example of Brady, and there were further example by Loda and Kropoller. And recall that being of type Fn means that H is of type Fn if there's a classic space for H, which is a complex with finite n skeleton. Okay, so we consider n at least 3, so Fn implies F2, so all these things will be finitely presented, and they are a bit better than this. So okay, so for n equal 2, this was answered in 1999. For n equal 3, we answered the question in a 2021 paper. So I will write lim. So this is Claudio, Llosa Isenrich, Bruno Martelli, and myself. And so this relied on the work of Italiano Martelli Migliorini. So we use this 8-dimensional hyperbolic manifold that this polytope that we heard of in the previous talk. We used some cusped real hyperbolic 8 manifold and plus some Denfielding arguments, as in the previous talk, to give infinitely many examples of hyperbolic groups containing subgroups which are F3, not F4. Okay. And now, so this also relied on Brady Morse theory. And what becomes tricky in large dimension in Brady Morse theory is that you have to understand the topology of links. And already in dimension 8, it's complicated. Sometimes you need a computer to help you. And so in large arbitrary dimension, I don't know how to do this. So we will answer this question, but it will not be using Brady Morse theory. Maybe someone will be able to do it using Morse theory Bezdina Brady Morse theory later on. But the equivalent of this in classical Morse theory, and I will explain this later on, is just to have Morse function with where you understand the indices of critical points. So you want to prescribe the indices of critical points. And we will see a nice way to do this using complex geometry. But okay, I will state a theorem now. This is a joint work with Claudio. So we take a lattice in PUM1. So this is a group of holomorphic isometries of complex hyperbolic space, or complex holomorphic isometries, or holomorphic automorphism of the unit ball in CM. We want it to be cocompact and arithmetic, and we'll use this at some point. And we want it to have positive B1. And the theorem is that if you take a deep enough finite index subgroup, so there is a subgroup of finite index such that whenever you go, you can take gamma naught or anything deeper. So for any gamma 1 in gamma naught of finite index, there is, you look at the H1 of gamma 1. So you should think that this is a huge dimensional. Okay, it's known that when you have an arithmetic group like this, it's known that if B1 is positive, then the virtual first Betti number is infinite. So you have finite index subgroup with very large B1. And what we say is that there is a dense open set of non-zero classes, such that whenever you take a class in this open set which is rational, so this means that it's isomorphism from gamma 1 to R, and its image is cyclic, then the kernel is exactly like this. The kernel is Fn minus 1 and not Fn. Actually, not Fpn of Q. Okay, so this n is an M actually. Okay, so this is really the complex dimension of the manifold we started. So I will try to explain the proof of this today. I will mention other theorem, but I'll try to give a more or less complete sketch of the proof of this. So in particular, the sensors based on Brady's questioning for all n. Okay, some comments. Our first comment, maybe I'll not explain, but I mean, I cannot explain in this talk, but such lattices exist. So this is a theorem of Kashdan. So if you just take the simplest arithmetic construction of lattices in PUM1, they will give you lattices with positive, virtually positive B1. Okay, so think of something like this, a field like this, and the Hermitian form you take. Okay, just a classical construction, a Hermitian form like this. You put a square root of 5 somewhere, and you look at the matrices preserving this Hermitian form with entries in the ring of integers of this number field, and this is a cocompact lattice, and it's known to have virtually positive B1. But already at the very beginning, it's not explicit because Kashdan tells you there is a congruent subgroup with B1 positive, but okay. And second thing, second comment, that at least philosophically, what we do is related to the work of Hilak and Fischer. Why? Because we have a group, and what we say is that, I mean, I will explain. So the kernel of a morphism like this, it can never be FPM of Q, even if you take a morphism to Z2 or Z to the K. One way to see it is to use L2 Betti numbers. So what we say is that for a generic morphism, the finiteness properties of the kernel are as good as allowed by L2 Betti numbers. And this is what Fischer proved in another context for other groups and with different finiteness properties, but it's kind of the same philosophy. So the kernel of a generic morphism, I mean the finiteness properties, are as good as allowed by the L2 Betti numbers of the ambient group. So in the work of Killack and Fisher, they consider Riefers groups. Here we don't know if these guys are Riefers. And the techniques are different, and also they work with FPM of Q, so they don't get FM -1. But yeah, philosophically it's a bit the same. Okay, so I'll just mention a few more theorems before explaining the proof of this. So another theorem is that for the same gamma 1, so you take an arithmetic lattice.
They're not cumulative, but so what do you mean as good as allowed? As if they were cumulative, like the rules, like.
Okay, if you have I will talk about this later, but okay. If you have something like this, it follows from a theorem of Lux that if this guy has an L2 Betti number which is non-zero in dimension I, this guy cannot be FPI or FI.
For not, you don't need.
Yes, so the finiteness properties of this cannot reach the level where there is some non-vanishing L2 Betti. Okay, so the same techniques also will give us homomorphism to Z2 with kernel of type Fn -1. Okay, so now you can ask, okay, but these groups, they are lattices in Lie groups. Do you have more hyperbolic groups having these properties, having some groups which are Fm -1, not Fm for arbitrary large M? Yes, they are. So I will just mention one thing, but the group I will talk about now are even, in some sense, less concrete than these lattices. So even harder to build, but still I want to mention it. So there's a.
Yeah, this would sound like a lazy question, but going from 2 to 3 is a problem.
We don't know the answer for k greater than 2. So this comes naturally using the theory of BNSR invariance, but I don't know the answer for k greater than 2. More questions? Okay, so there is a recent paper of Stover and Toledo who what they do is that they show that there exists for arbitrary dimension, there exists a closed Keller manifold of dimension m with a Keller metric of negative curvature, not homotopy equivalent to a locally symmetric space. LSS means locally symmetric space. And I could call this theorem C, but I will not write it. So theorem A and B also apply to some of these closed Keller manifolds. So instead of gamma, which is a lattice in PUN1, you could take the fundamental group of these guys. So it gives further hyperbolic groups with these properties. But there's one non-trivial thing that you need to use to build these examples. These guys are ramified covers of arithmetic ball quotients, but to know that these ramified covers exist, to build a ramified cover at some point, well, you need a totally geodesic submanifold so that the ramified cover will be nice, but to build a cyclic ramified cover, you need the homology class of your manifold to be divisible by something. And to get example of ball quotient where you know that some homology class is divisible, you have to use hard stuff about the homology of arithmetic groups. But okay, so theorem A and B also apply to some example of Keller manifolds like this. Okay, and I will mention two more results, and then I will explain the proof of theorem A. So the next result is that if you take an arithmetic lattice in PUM1, so arithmetic, cocompact, and with B1 positive, then its M's BNSR invariant is empty. So what is this? It's the Ems-Bierry-Neumann-Strebel-Renz invariant. And maybe I will define it towards the end of the talk. I will not really do it, but it's a subset. In general, this thing is a subset. So you look at the H1 of your group, you remove 0, and you don't projectivize, you only divide by a positive scalar. Okay, you identify two characters, two classes if they differ by a positive number, and this thing is a subset of the sphere. This is a sphere, and the sigma n, it's a subset of the sphere which is related to being FPM for the kernel of the guide. I mean, maybe I will explain the relation, but okay, so the set is empty for these lattices. Okay, and the last thing I want to mention, so using Moore theory, we study finiteness properties of kernels of homomorphism to Z or to sometimes to ZK, and we still with Claudio, we realize that we can produce with the same kind of technique, we can produce a non-normal subgroup, not in a hyperbolic group, but a non-normal subgroup with exotic finiteness properties. So what I'm claiming is that there is a cocompact lattice in PU21, and the surface, and the subgroup of the direct product, which is not normal, and H is F2, so finitely presented, not FP3. And this guy comes from a fiber product construction. You have your surface group and you have gamma, and these two, we build an example where these two guys map to another surface. So two surfaces here are hyperbolic, and H is just the fiber product. So just to say that, well, it would be nice to have more examples of subgroups with exotic finiteness properties beside all these kernels of homomorphism to abelian groups. And so we have one example which doesn't sit in a hyperbolic group, but okay. Okay, so now let me try to explain where all of this come from. So to prove theorem A, you can either use the BNSR invariance or just do classical Moore theory. So I will do classical Moore theory because it's a bit simpler. So where do these results come from? So suppose you have an even dimensional manifold. Okay, so suppose you have X, which is closed, spherical, 2K dimensional. And suppose you have a map to the circle, and which is a Morse function. So locally, it's like the differential. It looks locally like a Morse function. And I will ask that all its critical points have index equal to K, to the mid half the dimension. So it's good because if you don't know the definition of the index, if you don't remember if it's the number of positive eigenvalues or negatives, and you don't care. We just look at the middle thing. So assume all critical points of F have index K. And then the proposition, which is classical, it's the same thing as in Brady Morse theory. Then the kernel of the induced map on pi1 is Fk minus 1. Okay, and not Fpk of Q if you add something. If, for instance, the Euler characteristic of X is known. Okay, so where does this come from? Well, you look at the cyclic cover induced by this thing. Let's call it X hat, and you look at the Morse function F hat, which lifts your F. So first, for the second point, I'll prove the second point first. Well, if you know that X is a locally symmetric space, and you know what is the behavior of L2 Betti numbers, you can deduce it from the theorem of Luke I mentioned before. And this even applies to morphism to ZK. But if you have a homomorphism to Z, there's another argument that Henry loves and celebrates, I think, since he heard about it. So there's an old paper of Milnor called on infinite cyclic covering. So he does not theory, but actually this paper, you can apply it to define less properties. And what Milner proves is that if the Euler characteristic downstairs is non-zero, then the homology of this infinite cyclic covering is infinite dimensional in some degree. Okay. And if you're on a manifold using Poincare duality on intermediate covers, you can see that actually this must be infinite dimensional in some dimension less or equal to k. So there exists an I smaller than k such that the homology of this cover is infinite dimensional in degree I. Okay, and this X hat is the classifying space for the kernel of this homomorphism. So this prevents your kernel to be FPK. Okay, if you have PK, all the homology up to degree k will be finitely generated. So this proves the second point. So if you don't care about just for this, you take a manifold or a finite complex, a cyclic morphism from the pi1 to z, and you look at the cyclic cover, and if the Euler characteristic downstairs is non-zero, then this is true. So he builds an exact sequence relating the homology of this and the homology downstairs and the action of the Dex transformation. Okay, and for the first point, well, the first point is if you understood last week's courses, you should be able to prove it yourself. Okay, so how does it work? You start with a smooth fiber, and you want to relate the topology of the fiber to the topology of the thing. So this has the right pi1, the pi1 we want to study, the kernel of the morphism, and all the higher homotopy groups are 0 because we started with X, which is aspherical. And when you secant the fiber, you have to understand the change in topology when there are critical points.
I listen to the pitch and what the full FK minus 1.
So I've proved this with the Milner argument. Now I will do the first part. Now I will do this. So when you pass a critical value, morph theory, classical morph theory tells you that so the preimage of some interval like this, if there is, I don't know, one critical point here, it has the homotopy type of this fiber with a cell of dimension k attached to it. Okay, so up to homotopy, it's like this fiber with some k dimensional cell attached. And so since I assume that all the critical points have index k, X hat, it has the homotopy type of the fiber plus infinitely many, well, if there are some critical points. Okay, so in particular, you kill some spheres, some k-1 dimensional sphere, but in degree lower, you do nothing. So for instance, if k equals 2, this implies that f is connected. And pi1f surjects onto pi1 of X hat. So it gives you that the kernel is finitely generated. And in higher dimension, what you get is that the fiber has the right pi1 and has 0 homotopy groups in the right interval. So up to k-2, if I'm not mistaken. Okay, so you can, well, I mean, I'm already done. Basically, you see that you have a classifying space, which is like something compact plus some cells of dimension k. So your group is of type fk-1. Okay. So this proves the proposition. Okay, so now the question is, how do you build aspherical manifolds with plenty of classes like this? So how do you build examples of even dimensional manifolds as before? So meaning, morph function to the circle with the only critical point of index k. And the answer is there is a nice way to do this. It's to use complex geometry. So how do you do this? So suppose X is a complex manifold. And you have alpha, which is, well, I will explain how to build this cohomology classes like this, maybe not integral, but having a only critical point of index k, it's an open property. Okay, if you have one form which is Morse, even if it does not represent an integral class, you can perturb it. It's still Morse, and you will have a control. I mean, and the indices will not move. So suppose you have a holomorphic one form. So it's a one form which takes complex values. And I will assume that it is Morse in the complex sense. So what does this mean? It means that near a critical point, near 0, we assume that it looks like this, well, like the differential of something. And where this function f, you can find complex coordinates such that it's a sum of squares like this. Okay. So assume that you have an alpha like this, and near every 0 of alpha, you have this picture. You have coordinates like this. And then you are happy because what is the real part of this? Well, if zj is xj plus I times yj, then the real part of f is the sum of the xj's minus the sum of the yj's. Okay, let's call k the dimension. So if you have a holomorphic Morse function, which by definition means something which looks like this, then its real part is a real Morse function with index half the dimension. And so the real part of alpha will be, it will be a class like we like, except that we don't know that it's integral, but this we can achieve by perturbation. So this class will be represented by a Morse one form, all of whose critical points have index k. So this is basically the idea. And we need a little bit more. And if the claim is that if alpha is maybe not like this near the critical point, but if it has only finitely many zeros, then the real part, it is still true that the cohomology class of the real part, you can represent it by a form with only critical points of index k. Okay, so recall that k is the complex dimension of the manifold we are looking at, or half the real dimension. So I will not explain this, but this, you just need to know a bit of complex analysis to do this. You can just perturb a bit near the zeros to an isolated zero like this. It will come with a multiplicity, and you can perturb to replace 1 0 by finitely many non-degenerate zeros. Okay, so now I have to explain how to build complex manifolds with lots of holomorphic one forms like this. So with a lot of holomorphic one forms with finitely many zeros. Okay, because if I have this and I take the real part of these classes, maybe they are not rational, but I perturb so that they are rational, and I get maps to the circle like we want. And also observe that up to now, at the beginning in theorem A, I said that the lattice was arithmetic. I have not used arithmeticity so far, so I will use it at one point a bit later. But so far, it's just a complex and Keller geometry. We don't use arithmeticity. Okay, so now I will assume that X is a Keller manifold. So you can think of X being just a submanifold of some complex projective space. So it just means that you have a complex manifold on the Hermitian metric, and the Riemannian and complex structure are compatible. So the imaginary part of the metric is a closed form. This is the definition, but okay. And the good thing when you have a Keller manifold, a closed Keller manifold, is that you always have a complex torus. So there is a complex torus. So its real dimension is equal to the first Betti number of X. Its complex dimension is half the Betti number of X. And the holomorphic map from X to A of X. And okay, I should say something else. And this induces an isomorphism on H1, okay? H1Q or Z modulo the torsion, as you want. And all the holomorphic one form on X, they are pullback of some form on the torus. Okay, and the one form on the torus, they are just linear forms.
I think that's so for a third band expand. There is no.
A Riemann surface?
Yeah.
So this is just the Jacobian manifold, the embedding of the Riemann surface. So in general,
I don't know what that is.
okay, okay, I can tell you later. Right. Okay. Okay. What is this thing? I can maybe I will use it if I have time. So this torus, what is it? It's just you look at the space of holomorphic one form on your X, and you take the dual. This is a vector space, and you mod out by a lattice. There is a way to send this or H lower one rather inside this so that it's a lattice. And what is the map? I can tell you what is the map. You have X. You fix a base point. So this thing will be defined only up to translation. And you take a path from your base point to X. And this is just, I will tell you what it is in the universal covariant. This is just the linear form on one form, which is integration on gamma. In other words, you take a complex form and you integrate it on gamma. So this lives in the dual of the space. And this is, I mean, for Riemann surfaces, people describe it not like this sometimes, but in high, yeah, this is what it is. Okay, so now a proposition. I don't know when I started. Okay, cool. And I will still not use arithmeticity. This is still true for Keller manifolds. That assume that this map is finite. And what does this mean? It means that whenever you take a point in the target, the fiber is finite. And if this is true, then the forms, the holomorphic forms with finitely many zeros are dense. Okay, how do you prove this? Okay, we are on a Keller manifold, so if we prove this, we are happy because any class in H1 with real coefficient, it's a real part of some class here. So this will, just by looking at real parts, this will tell me that classes in H1, which are represented by a real Morse one form, all of whose critical point have index k, they are dense. So it will prove theorem A for this X. Okay, so we have you look at the set of zeros of a form, and if suppose it's not a finite set, so it's an analytic set. So if it's not finite, there's a Riemann surface on which alpha vanishes, maybe with some singular point, but and so you send the zero set into the torus, and since this map is finite, it cannot be mapped to a constant, this curve. So A of this singular set. So this has positive dimension and it's an analytic set. And now on a complex torus, when you have an analytic set, something defined by holomorphic equation, you can just, well, let's say we translate it so it contains zero. You can just take the subgroup generated by this. So I have this set, let's call it, I don't know, W. But the thing is that since since W is analytic, when I start summing points in W, it gives me an increasing family of subsets. I look at this, I don't know, let's call this WK. And it's just all the sum like this, W1, all the sum of K points minus K points in my set. All these guys, they are analytic subsets and they increase, so that it has to be stationary. So at some point, so the union of all these things for all K, it's a subgroup, but it's stationary. So you get a complex torus, and by definition, if your form alpha was the pullback of something, some beta, you will get that beta has to vanish on this torus. But now, so now this is the complement of this is a dense set. Okay, if you take a linear form on this vector space, I don't know, here, and assume that it's, for instance, this linear form takes a non-zero value on all elements of the lattice. then it implies that this linear form cannot be zero on the subtorus, because otherwise it would have zero period on the pi1 of the subtorus. And then the pullback of this form will have finitely many zeros. So, okay, so this is the argument. So the linear form on a torus which do not vanish when you restrict them to an arbitrary subtorus of positive dimension, this is a dense set. Okay, so if beta does not vanish on any subtorus, then alpha has finitely many zeros. Okay, and now let's go back to lattices. Okay, let me keep this formula. So now the last ingredient we need is a theorem due to Dieu, and it says the following. If you take a lattice in PUM1, or compact arithmetic, then you look at the quotient of a unit ball of CM by gamma. And then for what the theorem says is that after taking a finite index subgroup and looking at the quotient, then for this quotient, for this cover of the original X, the manifold, the map to this, it's called Albanese map, this map to a complex torus, it's an immersion. It's a finite map. Fibers are finite. And so if you sum up all pieces, it gives a proof of theorem A. So let me just explain a bit where this comes from. So this is not difficult. You should not be scared of the theorem. It's beautiful, but it's not difficult. So first, recall that there's something general about arithmetic group is that if you have an arithmetic group with Betti number j, which is too big mean greater than the jth Betti number of the dual symmetric space, or greater than the dimension of the G invariant form on the symmetric space, and if this is true, the virtual Betti number in degree j is infinite. So here B1 positive implies VB1 infinite. So I think, and the general statement for arithmetic groups, you can, I mean, there are 2 papers on arXiv explaining this. I think they're not published, but I think it's well known for people doing arithmetic groups. So there's a note of Hegel and another note of Venkataramana explaining this. And to do this, it's just, yeah, you use this idea. So if you think a bit about this formula, saying that AX is an immersion at X, it's the same thing as saying that you look at all holomorphic form on your manifold, you evaluate them at your point. Okay, so this is one form, and you just take its value at X. And saying that this is an immersion is the same thing as saying that this is onto. So basically, you want to prove that after taking some finite cover, given a point, you can always span the dual space by one globally defined one forms. And so basically, you look at the universal cover, there is some non-zero one form which comes from this quotient. And then you look at all the one form which are defined on something commensurable to gamma, and you take the vector space generated by this. And since you are arithmetic, the commensurator will act on the space, so we'll be able to have one forms which vanish everywhere and in all directions you want. And this is more or less the proof of the theorem. Okay, I will just say in 5 seconds something about the Z2 case, and then I will stop. When you have a homomorphism to Z2, there's a theory of BNSR invariant which tells you that the kernel is F something, K minus 1. If and only if there's a certain circle which is contained in sigma K intersection minus sigma K. And this circle is what? It's all the homomorphism you get by composing this with some morphism to R. It gives you a circle. And if you look at what I did, there naturally first, this thing, it contains the Morse form, the classes corresponding to Morse form with only critical point on index K. It follows from the BNS, the definition of these guys. And when you have a holomorphic one form with finitely many zero, you can multiply it by a complex number and it will still have finitely many zeros. So you naturally have lots of circles in this thing. Maybe they are not rationally defined, but you can perturb them. And okay, and this is the proof of theorem B.
I have a question.
Mm-hmm.
You said that you get infinitely many examples, right? With each property. How do you know that they're different?
The ambient hyperbolic groups?
No, the subgroup. So
the subgroup. No, the subgroup we didn't really do it. We didn't do it. So there are infinitely many ambient groups. This follows from the arithmetic groups.
Okay.
For the subgroup, I guess it's true. We didn't do it, but
I said like so the different maps could be the same.
Yeah.
you want not isomorphic. Yeah, but I mean, if you have the big group, it's quite rigid. You have most rigidity, and the subgroup is just a kernel of a morphism to Z, so it's quite big inside the lattice. So I'm confident. I mean, yeah.
But you mean not being the same.
Abstract reality.
No, so this is not written anywhere. We didn't do it, but okay. Go ahead.
Is it conceivable that there's not that this argument is not simple, but is it conceivable that there's a simpler argument specifically for arithmetic lattices of simplest type? I mean, it seems like you cared.
Well, first, the arithmetic lattices of simplest type, they are the only one which are known to have some finite index group with B1 positive. I mean, I'm not sure knowing if you add simplest type, you mean?
Yeah.
I don't know if it will help to have a simpler proof. Mahan?
Yeah, no, I just wanted you to repeat that argument you wrote. So you have this dimensional stuff on page where your form vanishes. To the
it's still positive dimensional.
Yes. And then what do you do? I mean, what
well,
to the game?
So your form alpha was the pullback of some form on the torus. So by definition, the form on the torus will vanish on the image of the set. And now you take the subtorus generated by the set.
No.
But since everything you were only dealing with analytic set, the subtorus, it will just be obtained by summing finitely many and subtracting.
But how do you get this on the subtorus? This
Exercise. I mean, it vanishes on the image, so it vanishes.
Okay. Because you're using the group structure in the algorithm.
Yes. I mean, this. Yeah, I mean, this kind of idea, it already appears in a paper of Simpson of 30 years ago.
No further questions. Let's thank Pierre again.